Right. Good evening, everybody. There's a couple of seats down the front if you want to come and... Yeah, come on down, as they say. That's right, there's a few there, and there's a couple down here, so... Right, very good. Packed hall, this is what we like to see. So it must be something to do with that title, I think. Waking the Giant. So. Okay, welcome to the Geological Society of London, and to this, the 10th 2016 Society London lecture, entitled Waking the Giant, How a Changing Climate Triggers Earthquakes, Tsunamis and Volcanoes. My name is Malcolm Brown, and I'm President of the Geological Society. And one of my pleasures of this job is to introduce the speakers. And today's speaker is Professor Bill McGuire of University College London. An astonishing transformation over the last 20,000 years has seen our planet flip from a frigid wasteland into the temperate world upon which civilization has thrived. This dynamic episode in Earth history saw the crust bouncing and bending in response to the melting of the great ice sheets and filling of the ocean basins, triggering earthquakes, spawning tsunamis, and provoking lively responses from volcanoes. Now there are signs that human-induced climate change is encouraging the sleeping giant to stir once again. Bill McGuire is Professor Emeritus of Geophysical and Climate Hazards at UCL, a science writer and broadcaster. He was a member of the UK Government Natural Hazard Working Group, established in 2005 after the Indian Ocean tsunami, and in 2010 a member of the Science Advisory Group in Emergencies addressing the Icelandic volcanic ash problem. In 2011, he's one of the authors of the IPCC report on climate change and extreme events. His books include A Guide to the End of the World, Everything You Never Wanted to Know, Surviving Armageddon, Solutions for a Threatened Planet, and 7 Years to Save the Planet. His latest book is Waking the Giant, How a Changing Climate Triggers Earthquakes, Tsunamis and Volcanoes. Bill's presented the Radio 4 series, Disasters in Waiting, Scientists Under Pressure, at the End of the World report on Channel 5 and Sky News. Bill lives and runs and grows fruit and veg in the Peak District, high up, you see, he's not daft, where he resides with his wife Anna and 2 sons and 3 cats. Ladies and gentlemen, please welcome Professor Bill McGuire.
Thank you very much. You can see from the titles of my books that you're not going to leave this place happy at the end of the talk. I'm going to talk about what it says on the tin, really, how a changing climate triggers earthquakes, tsunamis and volcanoes. But before I do, I want to start off with a quote. Here we are. Sometimes you see beautiful people with no brains. Sometimes you have ugly people who are intelligent, like scientists. It's always great to know how people think about you when you're standing up there in front of an audience. But the funniest thing is who actually said that. It was the former Chelsea manager and now Manchester United manager, Jose Mourinho. And apparently he was trying to explain that the pitch at Stamford Bridge when they were playing Barcelona wasn't as bad as it looked. And this was the best thing he could come up with. So I'll leave it up to you to decide how ugly I am. But am I mad? That's the question. I mean, surely climate change is linked to the atmosphere, the oceans, but how can it actually affect the solid Earth? Well, the first thing I should say is that this isn't a pet theory of mine. This is there's been a lot of research undertaken on climate change and the solid Earth. We've got lots and lots of evidence, particularly going back to the period after the last ice age. So, I hope you'll realise I'm not mad, and this isn't just some strange theory of mine. So, as I said, if we go back to the peak of the last ice age about 20,000 years ago and look at the warming that happened afterwards, so we see lots of evidence for climate change triggering geological events. We also know from studies today that very, very tiny changes in the environment can trigger geological events on a completely different scale. So, for example, literally, the pressure of a handshake can trigger a major earthquake if the fault is ready to rupture, ready to go. So that's something that provides added impetus for this idea of climate change linked to the solid Earth. We also know from looking at places like Alaska that climate change is already triggering a geological response to the solid Earth. We're beginning to see earthquakes related to ice loss there, for example. We're beginning to see more landslides. And finally, there's more and more research going on in terms of modelling what might happen in the future, or what we expect to happen in the future, as we see major ice sheets melting, as sea levels rise, and this sort of thing. So there's a lot of research going on at the moment that you can follow up if you wish. And here are three of the sources. On the left there is a thematic issue of the Philosophical Transactions of the Royal Society, which I edited with a few others in 2010. Now that looks at different aspects of what's called climate forcing of geological hazards. Those are technical papers, obviously there's about a dozen altogether. In the middle there is the Intergovernmental Panel on Climate Change's report on extreme events and climate change, which for the first time includes a solid Earth response. If you've seen IPCC documents before, you won't be surprised to know that this is about this thick in print, but I think you can access it online. And then if you want the popular version, which again, though, is based upon about 100 scientific papers, there's my book, Waking the Giant, which people this afternoon at the matinee could buy, but unfortunately they've sold out now, so you'll have to order it online, should you choose to do that. So there's a variety of sources at different levels which you can access if you wish. In terms of the talk, I'm going to concentrate first of all on looking back in time to that period between the height of the last ice age 20,000 years ago and our much warmer climate today, and how climate change and the solid Earth are linked. I'll say a little bit then about where we are now, what sort of responses are we seeing now in different parts of the world. I'll look ahead a little bit to the future, and then I'll finish off talking about what I've called the last straw, which is this idea of a tiny little change in the environment triggering a geological event, which can be disastrous. Now, I am going to say a few words about climate change to get things moving. And this slide, I think, says it all in terms of is climate change happening or not. It shows the temperature trend for the planet over the last 10,000 years. We came out of a glacial period. We're heading back into a glacial period. And our temperature, global temperature, should be somewhere down here. And that's the way it was heading until maybe a century or so ago. Now, it's up here. This is a completely unnatural trend. It's caused entirely by a 40% plus increase in carbon dioxide, the main greenhouse gas in the atmosphere. Here are another couple of figures that are slightly scary. Just look at the top two, not the bottom two. But these show predicted temperatures for the end of this century for the world. On the left, you have an optimistic pathway, and in terms of greenhouse gas emissions. On the right, you have a pessimistic one, and that's pretty much the sort of trend we're on at the moment. Now, one of the reasons I think that many people don't regard climate change as being particularly worrying is because they see figures like 2 degrees C global average temperature rise, 3 degrees C, and they think, well, that doesn't sound like much. I could quite do with it being 2 or 3 degrees warmer. But that hides a multitude of sins, because that's an average for the planet. And a 2 or 3 degree global average temperature rise at the poles would translate into 5, 6, 7, 8 degrees C. And remember, the poles are where all the ice is, or 99% of it. So what this shows here in particular is how that global average temperature change for maybe 4 or 5 degrees in this case can translate up here in the temperature rises of 10, 11 degrees. Now, under these conditions, it's difficult to see how the Greenland ice sheet, for example, can survive for any length of time, geologically speaking. So that number, that 2, 3, 4 degrees, is an average. So always remember that. And where all the ice is, it's a much higher figure. Now, there's a load of information on here, which I'll go through bit by bit. You may have heard, well, I'm sure you'll know that there was a Paris conference nearly a year ago now, just over a year ago, actually, at which various countries came together and all said, great, we'll cut our emissions and we'll sign pledges to do this, that and the other. We'll keep the global average temperature rise below 2 degrees C, which is regarded by many as the dangerous climate change guardrail. In other words, beyond that, it becomes all pervasive, affects everyone and everything on the planet. Although obviously there's no limit above which everything changes. It's a gradual thing. So there's 2 degrees. That's what we're trying to keep below. This year, global average temperatures will be 1.2 degrees C above pre-industrial levels. One of the things they talked about at Paris in their optimistic backslapping or whatever is that they might even be able to keep global average temperatures below 1.5 degrees. No chance. whatsoever of doing that. And in fact, most climate scientists, I think, would say 2 degrees C is also extremely unlikely, very unlikely that we can do that. I'll come back to this right at the end of the talk. You might sometimes see this 2 degrees C dangerous climate change guardrail linked to the amount of carbon dioxide in the atmosphere in parts per million. And quite often you'll see, if we want to stay below that, we need to stay below 450 parts per million CO2. Well, we breached 400 last year. We'd like to be on this path, obviously, but unless something changes drastically, despite Paris, we're still going to be coming up through here and breaching that 450 ppm mark at some point. And adding to that, a UK Met Office study showed that even if we keep levels of carbon dioxide below this, there's still only a 1 in 5 chance of keeping temperatures below this. So the picture, despite Paris and despite all the good things that are going on in terms of renewables, renewable investment and this sort of thing globally, we're still not doing anywhere near enough to bring climate change under control. So to the meat of the talk, if you like, if you were hanging in space above the Earth 20,000 years ago, above the northern hemisphere, this is what it would look like. There's Greenland, you could just make out under there. You have huge ice sheets covering North America, Northern Europe, much of Northern Asia. These ice sheets are 2 to 3 kilometers thick, and they lock up enormous amounts of water that would otherwise have been in the ocean. So this is the height of the last glacial period. Now, between 20,000 years ago and around about 10,000 years ago, the Earth underwent a staggering change in its climate. It went from, temperatures went up by 6 degrees C. That's a global average again, remember. We replaced a cold, arid climate with a warmer, wetter climate, generally speaking, of course. And this is a staggering figure. 52 million cubic kilometers of water was shifted from those big ice sheets and dumped into the oceans. That's a staggering amount of water. So you lost these big ice sheets, 2 to 3 kilometers thick. They disappeared over a period pretty much of 10,000 years, not much longer than that. Sea level rose by up to 130 meters as a result of all that water being dumped into the ocean basins. And the change of mass, the redistribution of mass around the planet, actually lengthened a day by about 4 seconds. And the reason for that is that all the mass that was concentrated up here is now spread out across the planet. And it's exactly the same as a figure skater who's spinning very, very rapidly, slows down by throwing her arms out like this, exactly the same principle. But it just gives you some idea of the scale of the change that it affected measurably the length of the Earth day. Now, what happened at that time? What happened when all those ice sheets disappeared and the ocean levels rose? Well, let me start, first of all, up at high latitudes where these big ice sheets were located. This is what happens if you have a 2 or 3 kilometer thick mass of ice sitting on top of the Earth's crust. It depresses it. The weight, the sheer weight of the ice is so enormous that the crust is pushed down, and in fact the upper part of the mantle as well underneath. And it's pushed down to maybe 200-300 meters in some cases. So this is not insignificant. Now that you might think is interesting, but it's more than interesting if underneath the ice you have active geological systems like volcanoes, so you have magma coming up underneath there, and you have faults which are accumulating strain over time, and which now and again rupture to generate earthquakes. If you stick 2 to 3 kilometers of ice on top of these things, they can't operate. So volcanoes will not expel magma through that amount of ice. Active faults will continue to accumulate strain very, very slowly, but they won't be able to get rid of it. So that will just go on and on accumulating over tens of thousands of years in the case of the last ice age. Now, I'm sure you can imagine what happens when the ice melts. The crust comes back up again, bounces back. It's called postglacial uplift. And at the same time, because of that, the load on these faults and these volcanoes is released. Now, the faults may have accumulated 50,000 years worth of strain. And when that's released, they rupture, they generate massive earthquakes, much bigger than you might expect for these sorts of regions. And I'll come back to that in a minute. Similarly, magma stored magma is able to get out now, generating volcanic activity. Not only that, but as the crust bounces back up again and the mantle underneath comes up, the mantle is very, very hot and it's partially molten at the best of times. But if you reduce the pressure on it, which is what happens when it comes up, it will melt more and it will generate more magma. So you'll have even more magma coming up in addition to that which is stored. So you would expect, as these ice sheets disappear, to see a big geological response in terms of earthquakes and volcanoes, provided they're underneath the ice sheet, of course. The bouncing back's just like you rub a duck, incidentally. You just stick that down in the bath, let go, it comes back up again. It's not really that different in principle. And this really illustrates what's going on. You might not be able to see the detail, but this is actually an outline map of Scandinavia. There's Denmark there, Finland sticking out here, Norway and Sweden. These contours mark the amount of uplift that we've seen since the end of the last ice age. The Scandinavian ice sheet was 2 or 3 kilometres thick. The crust has bounced back by 275 metres in the middle there. So you're looking at a massive uplift across the entire region. And we see it in the UK as well. This is what the UK is doing at the moment. It's tilting. It's going up in Scotland and northern England, and it's tilting down in the southeast, which is why sea level, if you measure sea level rise in London, it's higher than it is in northern Scotland. And this is in response to a smaller ice, massive ice, which existed in this sort of area here. So it's a fairly common mechanism in places that have been glaciated, and we see it happening in North America and in other parts of the world as well. Now, this is the result of that ice melt and uplift. Here are 2 faults in Scandinavia, in Lapland, northern Norway and Sweden. This one here is fairly obvious because you can see the line of the fault, which is forming a cliff. This one you might not be able to see, but again, it's a cliff line here which marks the fault. Now, these faults are more than 100 kilometres long. There's a relationship, quite a straightforward relationship, between the length of a fault that ruptures during an earthquake and the size of the earthquake it generates. And for these faults to have ruptured in one go, which they did, must have resulted in earthquakes which are more than magnitude 8. Now, that is huge. You don't see magnitude 8 earthquakes in Lapland today. You don't expect them there. You expect them around the Pacific Rim or Southeast Asia, for example, but not in reindeer land, effectively. The reason these were so big is because the faults normally, without any ice, would have accumulated a little bit of strain, then had a little earthquake. Accumulated a bit more, had a little earthquake. But they couldn't get rid of it. It just accumulated and accumulated over the entire period of the last ice age. Then about 12,000 years ago, wham. Now that, again, you might think, well, that's interesting, but that's quite a long time ago, so it's not too much of a problem now, is it? Well, it might be, because some of the strain that accumulated during periods when ice covered parts of the landscape in Europe and North America might still be there and might still be awaiting release. There's a couple of examples here. There was an earthquake in 1356 which destroyed pretty much the city of Basel in Switzerland. That was bigger than magnitude 7. Again, an earthquake that you would never normally expect to see in Western Europe. And there is at least one school of opinion that suggests that the strain that was released during that earthquake was accumulated under an expanded alpine ice sheet. Obviously, the alpine glaciers would have stretched out far further at the height of the last ice age, and that this was strain left over from that, and that there may still be some residual strain there, which is a worry because Basel obviously isn't a small town now. It's a major city with industries, pharmaceutical industries and other industries. So even a magnitude 6 earthquake there would be a big problem. And this is an even worse woodcut here. North America, these shacks here have been knocked down by an earthquake in Missouri, a place called New Madrid, 1811 to 1812. There were a series of earthquakes, actually, over magnitude 7, maybe getting up towards magnitude 8. And again, these have been linked to the release of strain associated with the North American ice sheet and its melting. And again, you might think, well, that's interesting, so what? Well, there's a big debate going on in the US at the moment about whether there is still strain waiting to be released in the New Madrid area and whether it's still causing a big seismic threat. This is a big issue because this was Hicksville, USA in 1811. Now it is home to Memphis and St. Louis and major cities. And people there in businesses don't know whether to take out serious earthquake insurance because we have schools of thought saying there's no earthquake risk, and there's other schools of thought saying, well, I think that, there's a possibility of at least a magnitude 6 earthquake here. So these are legacies of the ice age. Go back to the ice age where we still may be seeing issues from that today. Now, as you will know from experience, 2004, the Indian Ocean tsunami, 2011, Japan, Where you get big submarine earthquakes, you can generate major devastating tsunamis. But you can get tsunamis generated in other ways as well. And one of them is by an earthquake that occurs on land, but which shakes off a submarine landslide. And that submarine landslide going into the sea can generate a tsunami in its own right. And this is exactly what happened as Scandinavia was bouncing back up again after the loss of the ice. Lots of earthquakes happening because the load on them at the faults has been released. One of those earthquakes triggered a massive submarine landslide. The back wall of the slide is about the distance from London to Manchester, to give you some idea of the size of this. And you can see it stretches 2/3 of the way towards Iceland or whatever. This generated a tsunami which, with run-up heights of up to 20, maybe even 30 metres in the Shetlands, 10 metres or more down the coast of Norway, 3 to 6 metres in eastern Scotland, and it would have come right the way down here. There's no evidence for it, or we haven't found evidence for it further south. It may have been the final straw that submerged Doggerland, which was an area of inhabited land in here that was still exposed as sea levels were lower at the time. And it would have headed westwards to North America as well. So clearly, if this happened today, it would be a devastating event for coastal communities all around this part of the world. 8,000 years ago, again, well, that's a long time ago. Is it a problem today? Well, it might be, actually, because this, you might be trying to figure out what this is here. This is actually a cross-section through peat in the Shetland. There's a dry stone wall of sorts up here, grass there, peat. This shell and sand layer is the tsunami deposit left behind by the Storiga tsunami as it just shot right across the Shetlands, which is very low-lying. But there are 2 other tsunami deposits exposed in the peat here, and the youngest one was placed in Roman times. So clearly, even 1,500 years ago, landslides were occurring, submarine landslides were occurring in this area, probably still associated with Scandinavia going back up again, that were causing tsunamis that could affect the UK. Now, whether we will see any more of those, I don't know, but later on, I will look at another tsunami risk in the North Atlantic, which will come from current climate change. But it's worth remembering that this risk isn't necessarily gone, even though the Ice Age finished 10,000 years ago or more. Now, I'm a volcanologist by training and inclination, so the volcanic response to climate change is always fascinating. You can't see it better than in Iceland, which is an island which is entirely volcanic, effectively. And we know the impact that volcanic eruptions in Iceland can have on the surrounding countries from the Eyjafjallajökull eruption in 2010, which cancelled something like 250,000 flights and cost a lot of money, €2.5 billion euros, I think, in terms of cost. And there's got to be people here who were stuck somewhere as a result of that. Anybody? Well, I didn't have to go far. But yes, it was a huge, I mean, that was a fairly small eruption, nothing spectacular, medium size. At the height of the last ice age, though, Iceland was completely covered by about a kilometre of ice. There it is up there. The ice melted rapidly as the Earth warmed, and then around about 12,000 years ago, there was a very significant volcanic response. The amount of volcanic activity went up somewhere between 30 and 50 times. And it lasted just not much longer than 1,000 years. So it was a sort of volcano storm, if you like. After that, everything settled down again, and we got into a level of volcanic activity like that we're used to today. But it's a fantastic example of a direct impact between climate change and volcanic activity. And again, I'll come back to volcanoes when we look ahead a little bit later on. Now, everything I've talked about so far is high latitude stuff, is to do with the ice sheets and what happened when they melted. But what about where all that water went? It all went into the ocean basins. So this is what I've looked at so far. The ice disappears from the ice sheets. Continental ice sheets bounce back. The continents bounce back as a result. But the ocean basins, when you dump that much water in, instead of bouncing back, they subside. And as a result of that, you get bending around the margins of the ocean. So this is the sort of thing that happens. Don't bother too much about lithosphere here. That's the crust on the very uppermost part of the mantle. So just regard that as crust for now. But if that's your coastline here, and this is the crust, and you dump an extra load of water on it, this is what will happen. And I've called it an action zone in here because you change the stress and strain situation such that you can promote the movement of faults, you can promote the movement of magma upwards into volcanoes, you can promote major landslide events because the slopes are getting steeper. So again, you start to see things happening as sea level rises and as you get this bending of the crust. This now isn't just confined to high latitudes, this is global. This is translating climate change and the effects of climate change to right across the planet, everywhere you have a contact with the ocean. So we're looking now at a global response rather than just a high latitude one. And if we expand that a little bit, if we look around the planet, what other sorts of effects have we got? Well, obviously, there are other parts of the world where there was heavy snow and ice cover. For example, on the volcanoes of South America, Chile, for example, these show a peak of activity at the time when the ice sheets which cover them, the thick ice covers, were melting. So we see the same sort of thing happening there as we did in Iceland. We even see a peak of activity in the Massif Central in France. There are volcanoes here, some of you may know, which are still regarded as active, even though they haven't erupted for the last few thousand years. But volcanoes can stay inactive for much longer than that. So we can get another eruption there in the future. But these show the peak of activity when the ice is melting in the nearby alpine ice sheet. Coastal volcanoes like Vesuvius here showed also an increase in activity, not to do with ice, but to do with sea level rising. There were some dramatic rises in sea level at the end of the last ice age, several meters in a century in some cases. And the extra load imparted by that rise in sea level seems to have bent the crust under these volcanoes just enough to allow magma to get out a little bit more easily. And we have a much better example of that operating today, which I'll talk about later on. And then you have faults as well. And the faults which seem most to have been affected by the rising sea levels at the end of the last ice age are ones like the San Andreas here, and also this one you may not have heard of, the North Anatolian fault. And they're faults that move sideways like this, and they're faults that parallel a coastline. And what seems to happen is that as sea level rises, so these types of fault get unclamped like this, and that makes it more easy for them to move. So faults like the San Andreas here seem to move more frequently and generate more earthquakes as sea levels go up and as sea levels are high. Also, there's been some work done on the North Anatolian fault here, which normally ruptures in bits. You can see the dates of earthquakes there: 1939, 42, 43, etc., 57. 1999 was the last one at Izmit, killed something like 17,000 people. The only bit left to rupture is the Marmara Sea stretch here, which is directly south of Istanbul and which presents a huge threat. This is one of the, probably along with Tokyo, one of the two cities under really serious and quite imminent threat from a big earthquake. But when the Black Sea was filling, at the end of the last ice age, obviously it was filling through the Mediterranean here, a piece of research has suggested that the weight of that sea next to the weight of that water next to the North Anatolian fault may have unclamped it such that the whole lot could have moved in one go. That would have generated at least a magnitude 8 earthquake and maybe bigger. So we're seeing a nice link between the loading caused by increased sea levels at the end of the last ice age and how some of these faults which parallel coastlines behaved. Now, everything I've talked about so far is back in time. It's all to do with coming out of ice age conditions into a warmer, wetter world. But what about today? And what about anthropogenic, human-induced climate change? Are we seeing any response already? Well, Alaska is sort of the canary in the cage in this respect, to use a mining term. It's what we see happening in Alaska is what we may see happening in other parts of the world later. It has lots of ice fields, some of the biggest glaciers in the world, the Bering Glacier here, the Bagley ice field, one of the biggest outside the immediate polar regions. But it's also very tectonically active, so there are lots of earthquakes, lots of volcanoes, so you have the mix of the two, which provides a fantastic field laboratory, if you like. And what is being seen in Alaska is that in places, 1 vertical kilometre of ice has been lost, which is an enormous amount. In just 100 years, a vertical kilometre of ice in some of these ice fields. And there's a clear link between the level of earthquake activity and the loss of ice mass above. There are lots of papers written about this. It's a very robust study. And it's not surprising. Again, if you have a fault sitting there with a kilometre of ice on, accumulating strain, you take that ice off, the fault's going to move much more easily. So it's not a surprise, but it is interesting that we're already seeing this response. The other thing we're seeing in Alaska are a big increase in in major landslides. These big black masses here are million cubic meter plus landslides, which are becoming increasingly frequent. The reason they're becoming more frequent is because it's only ice and permafrost that's actually holding these mountain faces together. And once that starts to melt and thaw, the mountain faces just fall off. And so that's becoming more and more common. It's also becoming more common around the world. In the Caucasus, up there, Kolka, in 2002, we saw a major landslide triggered during a heat wave, which generated a mud flow that traveled for over 20 kilometers. It wiped out several villages, killed over 100 people. But we're seeing this everywhere now, in the European Alps, in the Southern Alps, in the Rockies, more intense heat waves as a result of climate change, melting ice and thawing permafrost and causing big landslides. I mean, there are places in the Alps now, if any of you are climbers, where you can't climb in summer because it's just too dangerous, there's too much rock falling. So these are things that we're already seeing. We're starting to see big landslides happening around the world, which will be a big issue for ski resorts in the future, should there be any ski resorts, obviously, because there won't be as much snow. And we're starting to see this seismic response as well. But what are the future? Well, Greenland is a good place to look. That's what Greenland looks like if you were heading over it in space, in the space shuttle or the International Space Station. Ice covered, ice 2 to 3 kilometers thick, exactly the same situation as Scandinavia 20,000 years ago. But if you took all that ice off, that's what Greenland would look like. The weight of the ice is pushing down the central part so that it's below sea level. Now, obviously, you will know what's going to happen when the ice melts and melts more rapidly. The crust is going to bounce back up again. If there are any faults under there, they haven't done it. They haven't been able to release their strain for hundreds of thousands of years. And they will start doing so. In fact, I have colleagues who worked on this who have suggested that it might be possible to see a seismic response, as they call it, for Greenland within decades. So you might start to see earthquake activity happening. One of the staggering things is that Greenland is already bouncing back, not only just Greenland. Now, you won't be able to see what this is all about, but there's Greenland. These little coloured blobs here are GPS stations monitoring uplift of the North Atlantic, or just monitoring uplift or subsidence, whatever. But the red dots, you can see them on Norway and Iceland, Greenland itself, northern Canada. Those are GPS stations that are not only going up, but they're going up faster and faster. They're accelerating. And what this is showing is that the ice melt that we're seeing already on Greenland is such that it's causing the entire North Atlantic region here to start bouncing back again already, which is pretty staggering considering that the melting has really, geologically speaking, just got going. So this is exactly what the situation in Scandinavia would have been like shortly after 20,000 years ago. Now, what about Iceland? Iceland is not covered in a kilometre of ice anymore, but it has got a substantial ice cap in the east, the Vatnajökull ice cap. That is melting rapidly. Again, there's been work undertaken looking at how the loss of that ice cap, and it will go, will affect the level of volcanic activity, and not surprisingly, the level of volcanic activity will go up, which is significant in its own right, because the experience of just one small eruption from Iceland tells us that this could be a problem. And there are lots of volcanoes with unpronounceable names underneath Vatnajökull and around the margins, which can be affected by this. Again, it's already happening. These are contours here. You won't be able to read the detail, but these contours mark uplift of ice which is going on today. It's centred on the Vatnajökull ice cap, as you might expect. It's only going up by a few centimetres a year, but that's accelerating, and over time that will grow. And as I said right at the beginning, we know now these very, very tiny changes can trigger geological systems to do something if they're critically poised and ready to go. Further afield, what can we expect around the world as climate change continues to heat the planet? Well, where you have volcanoes like Mount Rainier in the Cascades Range in the western US, these are glaciated volcanoes, and the glacial ice is probably all that's holding some bits of these volcanoes together. So if that ice melts en masse, the risk of collapse of the volcano flanks goes up, what we call lateral collapse. And of course, places like Rainier have major inhabited areas around them, Seattle, Tacoma, etc. So this is a big issue for the future. Also, collapse of a flank can also trigger a full-scale eruption as well. If you go to South America, where you have snow-capped volcanoes like Solipoli here, as that snow melts, as water gets into the volcanic system, it increases the mixing of magma and water, which obviously is not something that you want to do, so the probability of explosive eruptions is increased. If we really see significant rises in sea level, rapid rise in sea level, then maybe coastal volcanoes like Etna will start to respond again, and we'll start to see more frequent eruptions going on. And then there's a special case really in the tropics. We know that tropical cyclones, hurricanes, typhoons, etc., have got significantly wetter over the last several decades. And one of the problems with volcanoes is they're covered in loose material, volcanic ash and debris. And if you dump a lot of rain on top of that, it can generate mud flows, and mud flows can destroy communities and kill a lot of people. And this happened with Hurricane Mitch in the late 90s. This is a Casita volcano in Central America. Rainfall triggered a slide here, which spread down the volcano and killed something like 2,000 people. So again, this is a specific problem for volcanoes in tropical areas. And what about earthquakes? Are we going to see lots more earthquakes? Well, probably not, because one thing I should stress, this is probably the best time to stress it, is that in most situations, climate change isn't going to cause an earthquake or a volcanic eruption that wouldn't have happened anyway. What it's going to do is it's going to bring the timing of that forward, so you get a clustering of earthquakes and volcanic eruptions as the Earth warms up. So it's not, it's only if a fault's ready to go or a volcano is ready to erupt, or the extra impetus provided by rising sea levels or ice loss or this sort of thing will push that over the edge. That doesn't mean to say we're going to have lots of earthquakes or lots of volcanoes erupting just for no reason at all. What we might see, though, are more, if anything, are more earthquakes at places of the type that we saw in Haiti in 2010. Now, this killed about 250,000 people, and it was another one of those faults like the San Andreas that moved sideways. And so rising sea levels, which tend to load one half of these faults and cause them to unclamp and move more easily, that could play a role in the future. But in terms of tsunami generating earthquakes, if anything, climate change is likely to limit those or to make them less likely, because obviously as sea levels go up and they add extra load to the submarine part of these faults, so they would tend to become more stable rather than become more likely to rupture. So that's a minor piece of good news, I suppose. And one place I haven't talked about yet is the Himalayas, which is worrying for a number of reasons. Obviously, the Himalayas contain a huge amount of ice. The ice is melting rapidly. It's generating meltwater, which has to go somewhere. The meltwater is ponding wherever it can and forming lakes. These lakes levels are rising. There are dozens of cases where there is a real threat of the lakes overtopping the barrier of rock or debris or whatever's holding them in. And obviously the communities down valley are under growing threat as a result of that. But there's an added dimension to this, because if there are faults underneath the glaciers that haven't erupted for a long time, that have been accumulating strain, as that ice is removed, it may allow those faults to move. They may trigger earthquakes, and the ground shaking may generate landslides into the lakes or shake the rock dam that's holding the water in, but actually bring on or bring forward the big floods that are expected to happen anyway. So this is a concern not specific to the Himalayas. There are issues also in the Andes and even in the European Alps, but the Himalayas it is the biggest of problems here. And this is one example I feel I ought to talk about, because it has the potential to be absolutely staggeringly devastating. This is a lake which wasn't there just over 100 years ago. It formed because there was an earthquake which caused a rock slide which dammed a river valley here. And so all this water, 16 cubic kilometres of it, has accumulated over the last century or so. At some point, that water is going to break through that dam. And when it does, it's going to travel and be destructive over distances of over 1,500 kilometres. So 5.5 million people are estimated to be under threat from the floods and the mud flows that will just surge down the valley and then gradually spread out into many other valleys. Now, this will go at some point, and the United Nations are aware of this, and there's a lot of talk about draining the lake and this sort of thing. But now, as with many of these things, it's all talk, and it'll probably still be talk when it actually happens. But again, like the Himalayas, the worrying thing is that this lake is fed by dozens of glaciers on the mountain peaks around here. As those glaciers are melting, so the lake levels are rising, and that in itself means that there's a better chance of the rock dam failing or being overtopped. But again, as the ice is removed, if that triggers any movements on the faults and triggers any earthquakes, they can trigger landslides into the lake, which can generate tsunamis, or they can shake the rock dam so it collapses, and that can trigger the outflow of the lake. And in fact, there have been 2 landslides at least since the lake formed, which have sent tsunamis up against the rock dam, but they haven't overtopped it yet. So this is just one example of how climate change may contribute to a really an unimaginable natural catastrophe. Coming to the last straw, this is really just trying to show you how these very, very tiny changes in the environment can and do trigger geological events which can be hazardous. Now, this is a fascinating volcano in Alaska, Pavlov. It sits on the coastline. It doesn't like erupting except generally during the autumn and winter months. And this seems to be, according to colleagues of mine who've worked and published on this, because weather conditions raise sea level by about 20 centimetres in the winter months. So sea level goes up a tiny little bit. But it seems to be enough to just bend, if this is a sea, there's a volcano, it seems to be enough to bend the crust just enough to force magma to the surface, like toothpaste from a tube, according to my colleagues. So that tiny little change every year is capable of triggering eruptions. In Montserrat, where I worked in the mid-1960s, I was going to say mid-1960s, mid-1990s, you have a lava dome here, which eruptions of which are triggered by torrential rainfall. Rainfall can, if you have torrential rainfall, it can squeeze into the cracks, it will turn to steam, it will open the cracks further, it will push further down, that'll turn to steam, until you have a runaway effect which triggers an eruption. So a nice relationship between weather and volcanic eruptions. Some more extraordinary cases here. Taiwan has, it's typhoon country, if you like. Loads of typhoons cross Taiwan. Typhoons have very low pressure at their hearts, and but you wouldn't think the pressure was low enough to cause faults several kilometres beneath the surface to move and generate earthquakes, but it is. So changes in atmospheric pressure cause faults to rupture and move deep down. Not huge faults, not big earthquakes, but the fact that it happens at all is extraordinary. And of course, if you have a major fault which is ready to go, primed and ready to go, as an eminent colleague of mine says, all you need is the pressure of a handshake. And he means that literally, to set it off. So the fact that storms can cause faults to move is staggering. And similarly, Japan, central Japan has enormous amounts of snow, even more than the Peak District. And when that snow melts in the spring, you get a seismic response. You see more earthquake activity as that load is taken off faults in the crust. Not huge earthquakes yet, but earthquake activity nonetheless. So this is quite fascinating. And what's even more fascinating is this example here. There is a volcano season, quite clearly. You get more volcanoes erupting between November and March than you do between March and November. And this is determined by colleagues of mine from Oxford and Cambridge more than a decade ago now for eruptions going back 300 years. All the eruptions we've got records of. And it's attributed to seasonal redistribution of water mass. So, as you'll imagine, in the winter you get lots of water locked up as snow and ice in the northern hemisphere, then it melts back in eventually into the oceans, and southern hemisphere winter, then the northern hemisphere winter. So this happens year after year after year, and the same thing happens. And GPS measurements have shown that distribution of water, redistribution every year, changes the shape of the Earth, just very slightly. So that it's like the Earth's beating every year. And the strain, the waves of stress and strain travelling around the planet every year as a result of that seem to trigger volcanic eruptions in different places when those eruptions are ready to go. And it seems that the conditions during November to March are more favourable than the conditions for the rest of the year. So the lesson here is if the annual redistribution of water can cause a volcano season, what are the much bigger changes, although longer-term changes, that climate change can and will bring in the future? What are they going to do? What's their geological response going to be? Now, I'm pretty much finished now. I'm not an optimist, as you might have noticed. And there's been a lot of fuss recently, especially over the last year of this Paris conference and how we're all, emissions are going to be reduced and we're all going to be saved and whatever, notwithstanding a certain new president in the United States. Renewable energy, investment in renewable energy over the last year overtook investment in hydrocarbons. I mean, there's good news out there, but there's not enough of it. Carbon emissions have been relatively flat, global emissions for the last 3 years. Well, that's much better than them shooting up, but it's not enough. We're still emitting 36 billion tonnes of carbon dioxide into the atmosphere this year. Emissions are up 63% since 1990. So, it's not enough. We're not doing enough at the moment. What we need is a rapid fall, very, very, very quickly, in global greenhouse gas emissions. Particularly because it may well be that we've either passed the tipping points for preserving the Greenland and West Antarctic ice sheets, or we will have passed them before we actually take any serious action. And if that's the case, then we're committed to more than 10 metres of global sea level rise. And in fact, there's a consensus pretty much amongst people that have looked at the issue that we're committed now to at least a 5-metre sea level rise. Whatever we do, whatever action we take, that's enough to inundate all coastal towns and cities that we have at the present day. I suppose my question is, are we adding geological havoc to climate chaos? I keep trying to think of a term for this. I keep using icing on the cake, but it's not quite the right term, is it? But you know what I mean. And finally, 2 more slides. Finally, again, returning to Paris, the Paris love-in here. How fantastic it's going to be. Well, this is the reality. Going back to 1990, these are our emissions here. These are an estimate of what will happen to emissions if all the Paris pledges work perfectly. So they've been things haven't gone up much at all recently, but that's the path they would fall. And this is assuming all those countries do exactly what they said they were going to do. And what do you think the chances of that happening are? 0, I would say, or very close to it. So assuming they do, though, and that happens, this is what will have to happen to emissions if we're going to keep below a 2 degrees C global average temperature rise. And what do you think the chances of that happening are as well? 0. I don't think, I cannot see how we can possibly stay below 2 degrees C other than a zombie apocalypse, a pandemic that wipes most of us out in the next couple of years, or something along those lines. So, as I said, I'm not the most optimistic. And just to finish on an even less happy note, if we burn all our fossil fuel reserves, or most of them, not even all of them, a paper was published 2 years ago trying to work out how much the global average temperature of the Earth would rise by. And the figure that was arrived at was 16 degrees C. Now, the global average temperature of the world now is about 14, day and night.